Welcome everybody. Today we're going to be talking about one of the simplest and at the same time one of the most amazing results in abstract algebra, at least in my opinion, the Dedekind product theorem. We talked in one of our previous videos about computing the degrees of field extensions when you adjoin one element to a field. So if I take F to be a field, and alpha in some field extension is an algebraic element, then we said that the degree of the field F adjoint alpha over F is equal to the degree of the minimal polynomial of alpha over F. However, one can ask a question: what happens if you adjoin more than one element? So what about this degree? As you know very well, you can adjoin more than one element to a field. What that means, right? F alpha comma beta, that just means I first adjoin alpha and then adjoin beta. And in fact, I leave it as an exercise to you that the order in which I do it, in fact, doesn't matter. So I can first adjoin beta and then adjoin alpha. So I can just as well write F beta comma alpha. It actually is the exact same field. So the order doesn't matter. But as you see, if you want to compute the degree of such an extension over F, then you cannot just use this result because that only works for just one element. So if, for example, you want to compute the degree of Q adjoin radical 2 comma radical 5 over Q, how do you do it? So this is where the Dedekind product theorem comes useful. And today we're going to be talking about the statement of the theorem and about some applications of it to computing degrees. So what's the Dedekind product theorem? So you start with a finite extension K of F. So you have a situation like this. You have your field F, and then you have an extension of it, K. So you have a field F contained in some field extension K, and the extension is finite, which means the degree of K over F is finite. In other words, K is a finite dimensional vector space over F. And then I take L to be a finite extension of K. So that means there's another field which contains K. And now one of the basic observations here that is crucial for the Dedekind product theorem is that, okay, well, K is a vector space over F, finite dimensional. L is a vector space over K, but also L is a vector space over F. We noticed in one of the previous videos that if you have a containment of fields, if you have a field extension, then the bigger one is always a vector space over the smaller one. So L is a vector space not only over K, but also over F. It will have probably different dimension over L and over K. But that's somehow the point of Dedekind product theorem, to relate these different dimensions. Okay, so we take a basis, L1 through Ln, of the field L. So these are some elements of L. And let that be a basis of L as a vector space over K. So that means every element in L I can write in a unique way as a K-linear combination of these elements, L1 through Ln. In the second step, I take elements K1 through Kn, which lie in K, and I take them to be a basis of K as a vector space over F. So these are elements of K, and K is a vector space over F, and the elements K1 through Kn give me a basis of K as a vector space over F. Then the theorem says this, that if you take the products of all the possible combinations here of the elements in L, in this set, and the elements in that set, if I take different combinations, I take their products. Now you can ask, well, where is that product here taken? What do I mean by multiplying an element of L times an element of K? Well, K is a subfield of L, so every element of K can also be considered as an element of L. So that means both the Li's and Kj's can be treated as elements of L. So I multiply them using the multiplication in the field L. Okay, so I get how many of these elements? Well, I have m choices for the L vectors and n choices for the K vectors. So altogether I get mn elements. And the theorem tells me that this is actually a basis of L as a vector space over F. Oh, so if that's a basis of vectors of L as a vector space over F, that means the dimension of L as a vector space over F is just mn, because the dimension is always the number of elements in the basis. So this is the dimension, right? That's the mn. L over K, well, that's the dimension of L as a vector space over K, so that's the size of that basis. And this is the dimension of K as a vector space over F, so that is the size of that basis. Okay? I already, of course, know that mn is m times n, therefore I can write this black expression here using the degrees. Okay, and this actually turns out to be a very, very useful expression for computing degrees of various extensions. So let's do that. Today we're just, in this video we'll only look at how to compute degrees of extensions using this theorem. And next time you will see how to actually use these computations to get a very interesting insight into which irrational numbers can be written as certain combinations of other irrational numbers. I will erase the statement of this theorem except for these for the statement about the degrees. So first, one notational remark. If you have containment of fields like this, and if F is a subfield of K, in other words, if K is an extension of F and L is an extension of K, then you usually do not write these containment symbols. Instead, people just use something like this. If the field K appears in the picture above field F, and there's a little symbol like that in between them, that just means K is an extension of F. Similarly, L is an extension of K. I can also write another one like this, which means L is also an extension of F. You can decorate this picture even more. What people sometimes write next to these symbols is the degrees. So here I would write the degree K over F. Here I would write the degree L over K. And this would be the degree L over F. And before I proceed to the first example, I wanted to make one observation that I want you to think about. Observation. If K is an extension of F, then the degree is equal to 1 if and only if K is equal to F. Okay, I'll leave the proof to you, but let me just explain a little bit why this should be true. I mean, imagine that I take a vector space over the real numbers and the dimension of the vector space is 1. Well, then that vector space is just a line. In fact, the real line. So every element in that vector space is a real number. In other words, this vector space is the same as the real numbers. So this just holds for every kind of field. If the dimension of K as a vector space over F is 1, that means K is just equal to F. Okay, with this insight, let's just look at some examples. Find this degree. In other words, find the dimension of the field Q adjoin radical 2 comma radical 5 as a vector space over Q. Just to remind you what that means here, you can watch one of the earlier videos to see what the definition of this is, but just to be sure, I can choose it in this order, and this is then my F. Then this is A0 plus A1 radical 5. Higher powers are okay, but actually you don't need them, because I know that the next one is going to be 5, the square, right? And then this coefficient can be absorbed into the first one. And of course 5 is rational, so in particular it lies in this F. So where A0 and A1 are in F. And remember what it means to be in F. F is Q adjoin radical 2, so that means A0 is B0 plus B1 radical 2. And A1 is C0 plus C1 radical 2, where all these B0, B1, C0, and C1 are rationals. So altogether I get B0 plus B1 radical 2 plus C0 radical 5 plus C1, and I get radical 2 times radical 5, so radical 10. So first we could make a guess. What is the degree of this extension? See, I need to, it looks like I have a spanning set, right? Spanning set. 1, radical 2, radical 5, and radical 10. From which I know that the degree of this extension must be at most 4, because I just need 4 elements to span this, this field over Q. This is spanning set over Q. So let's actually use the Dedekind product theorem to see that the answer actually is 4. So to do this, we're going to draw a diagram of fields just like here. So Q is going to be at the bottom, and then Q radical 2 comma radical 5 is going to be on the top. And then in the middle I can put in, say, Q radical 2. If I wish, I could go another way and I first do Q radical 5 over here. And note, by the Dedekind product theorem, this degree is equal to that degree times that degree. So if I can find, this is the one I'm looking for, right? This is the question mark here. If I can find this degree and that degree, or this degree and that degree, then if I just multiply them together, I get the question mark. Now these are easy. Both of them actually are easy. Because I know there are 2. Why is that the case? Because the minimal polynomial of radical 2 over Q is x squared minus 2, so is of degree 2. And just to remind you, right, if I join a single element to a field, then the degree of the extension is equal to the degree of the minimal polynomial. In this case, I know the minimal polynomial of radical 2 over q is x squared minus 2. So that means this degree is 2. It's this here, right? It's this, the degree is 2. So what about here? How do I get this field on top from this q adjoint radical 2? Well, what I do is I just adjoin radical 5. Oh, so I can just say, fine, so this must also be 2, because the minimal polynomial of radical 2 over q is again x squared minus 5, so it's degree 2. So I would like to say here that this is 2. Because the minimal polynomial of radical 5 over q is x squared minus 5, so is of degree 2. Well, maybe I would like to say that, but that's not entirely relevant. That is, this statement, which is true, does not allow me to conclude that that thing is 2. Why not? Think about it for a second. The reason why this doesn't work is because this field here is that field adjoint radical 5. So I need to know the minimal polynomial of radical 5 not over q. I need to know it over q adjoint radical 2. So how do I find the minimal polynomial of radical 5 over that field? So I argue the following way. So the point is, we don't know that, right? Is question mark. I don't know what the minimal polynomial is. So, correction to this. Correction. Radical 5 is a root of x squared minus 5, and this polynomial, well, yes, it has coefficients in q, but it also has coefficients in q adjoint radical 2 over x of x. Why is that the case? Because the coefficients of this polynomial are 1 and negative 5. Both 1 and negative 5 are rational numbers, and this field here, q adjoint radical 2, contains all the rational numbers already. So that means 1 and negative 5 are also elements of q adjoint radical 2. So this polynomial has coefficients in q adjoint radical 2. It's monic, it has coefficients in there, and it has radical 5 as a root. I just don't know if this is of the smallest possible degree. But because I found a degree 2 polynomial, then the minimal polynomial will have degree at most 2, because I already found one of degree 2. Maybe there is one of smaller degree, or maybe this is the minimal polynomial. If there is one of smaller degree, then the minimal polynomial will have degree 1. If there isn't one, if this is the minimal polynomial, then the minimal polynomial will be of degree 2. So this proves that the minimal polynomial of radical 5 over q adjoint radical 2 has degree either 1 or 2. So this degree is at most 2. Again, if you find a polynomial that an element satisfies, that is monic and has coefficients in the right field, what that tells you is that the degree of the minimal polynomial is at most the degree of that polynomial that you just found. We found a quadratic polynomial that radical 5 satisfies. It has coefficients in the right field, so the degree of the minimal polynomial of radical 5 over that field is at most 2. So that degree here is at most 2. But if it's at most 2, what can it be? It can only be 1 or 2, right? The dimensions of a vector space can only be positive integers, so it's either 1 or 2. So assume it's actually 1. Then, by our observation, these two fields are equal. Our observation said if the degree is 1, then the fields are equal. Which in particular implies, look, radical 5 belongs to this field. But if the fields are equal, that means radical 5 belongs to that field. So let us show that that's not possible. So if radical 5 belongs to this field, then radical 5 can be written as a0 plus a1 radical 2 with a0 and a1 in Q. That's what it means to lie in that field, right? Everything here is a combination of 1 and radical 2 with rational coefficients, and I don't need any higher powers, as we discussed already before, because the minimal polynomial of radical 2 over Q is degree 2. You only need to go to powers 1 less than the degree of the minimal polynomial. Okay, so this looks like it's probably not going to be possible, but we actually have to show that it's not possible. How would I show it? Well, I would square both sides. If I square both sides, then I get 5 is equal to a0 squared plus 2a1 squared plus 2 a0 a1 radical 2. From which I get that 5 minus a0 squared minus 2a1 squared is equal to 2a0 a1 radical 2. Note that the left-hand side here is rational. Because a0 and a1 are both rational. So the right-hand side must be rational. But I know that square root of 2 is not rational. So the only way the right-hand side could be rational is if it's 0. So I get that the right-hand side must be 0, which means a0, a1 must be 0. Yeah, you see, if a0 and a1 are not 0, are both not 0, then this is just a rational multiple of radical 2. So it's irrational. The only way this could be rational is if a0 or a1 are 0. So this implies that a0 is 0 or a1 is 0. Okay, so let's consider these two cases. Suppose a0 is 0. Then look at this. If a0 is 0, that means I have radical 5 equal to a1 radical 2, which implies that radical 5 halves is equal to a1 is rational. Oh, but what do I know? 5 is not a perfect square and 2 is not a perfect square. So 5 halves, the radical of 5 halves is not rational. Contradiction. Remember, we proved that for a square root of a number, of a rational number, to be rational, both the top and the bottom have to be perfect squares. Not the case here. So that's a contradiction. So now suppose a1 is 0. Then, okay, you can pause the video here and try to derive a contradiction in that under this assumption. Okay, and let me now show you how to do it. if a1 is 0, I'm looking at this again, then I get that radical 5 is equal to a0. Oh, but a0 is rational, so again I get a contradiction because radical 5 is not rational. Okay, so I got contradiction in both cases, which means this assumption was wrong. So that means, but I know that the degree is at most 2, and it is not 1, so it must be 2. So, hence, for conclusion, okay, yes, this was some work. Nothing comes for free in algebra. But we actually arrived at an answer. And now this 2 here, this 2, is okay because of that conclusion. The rest is easy because now I know about this 2 and I know about that 2. So the Dedekind product theorem tells me that the degree of this over that is this product of this and that. So I'm going to erase the statement of the Dedekind product theorem. So by Dedekind product theorem, I get that the degree of Q adjoint radical 2 comma radical 5 over Q is equal to this over Q radical 2. Okay, and this, all right, okay, how about this arrow? This is that, 2, and this is that, 2. So the answer is 4. Kind of how we maybe suspected at the beginning that the answer should be 4. Indeed, the set 1, radical 2, radical 5, and radical 10 that we wrote down at the beginning is linearly independent, so it is a basis. Okay, let's go to another example. Find, so this is example 2. Find the degree of Q adjoint